5.2, heat and temperature. This is a really short lesson in your textbook, but don't be fooled, it's really important. It just contains some tricky definitions. So let's go through it together. So remember, back in chemistry, there was the particle theory of matter. All matter is composed of tiny, unseen particles, and these unseen particles are in constant random motion. This makes sense, again, with what we just discussed with Brownian motion, that water molecules were moving in random patterns, hitting pollen molecules that then move in random patterns that we can actually see. Heat, also known as thermal energy, is the sum of all kinetic energies of all particles in an object. All right, what does that mean? So, if this particle is moving with lots of energy, and this one's moving with like quite a bit of energy, and this one's moving with like moderate amount of energy, and this one's moving with a lot of energy, again, they would all be moving reasonably close to the same amount. Like think if you were running the 100 meter in the Olympics. The athletes are fairly well matched. However, everybody runs at a slightly different pace. So you can kind of apply that analogy to our beaker of water here. Each particle is in this 100-meter race, and they're fairly well matched. However, there's going to be some that are running faster, moving faster, and some that are moving slower. So heat is the sum of all of their energies, their kinetic energies, and kinetic is their energy of movement. So if we were able to measure it, each particle, we would add up every particle's energy within this beaker, and that would give us the thermal energy of this beaker of water. Okay. Again, kinetic energy is the measure of the amount of motion particles have. So kinetic energy is energy of motion. Temperature and heat, they're closely related, but they're slightly different. Temperature is the average of all kinetic energies of all particles in an object. So, back to our 100-meter race analogy. If we were to add up all of the times, for instance, in our 100-meter and then average them up, we would get something that would relate back to temperature. Again, just adding up all of their times in our 100-meter race, remembering that some go faster and some move slower, would be our heat. Okay, so heat can be transferred. It cannot be directly measured. It's actually impossible to measure the kinetic energy of an individual molecule or particle and then add those up. Okay, so we can transfer it to something and we can measure how much is transferred by a temperature change. All right. Again, temperature can be measured. All right. And it is the average of all of these energies, and heat is the total, the sum, all of those energies. And the energies we're talking about each time is their kinetic energy, their energy of motion or movement. So in this example, which beaker has more kinetic energy? Well, each beaker has the same amount of water. This beaker is at 10 degrees Celsius, and this beaker is at 90 degrees Celsius. Because this beaker is warmer, the particles are moving faster. Therefore, this one has the greatest kinetic energy. Again, warmer means they have more kinetic energy. The practice here is on page 87. Take a look at number 1 and 2.